The theme of the lecture number 8, the electric field discrete charge distribution. We have six questions. The first question, electrical charge, the study of the definition of electrical charge, and we'll study on the formula and definition, physical definition of the Coulomb's law, and the definition of the electric field lines, and and here this is question number 4, motion of point charge in electric fields, and calculating electric fields from Coulomb's law, and final question and Gauss's law. Okay, we know electrical charge. We know of the different electrical charge, maybe electrical charge positively or negatively, but in here the first the study of the chapter of the physics, electricity and magnetism, and we know of the study of electricity has a history which includes the first electric lamp looked, and the electric, and from the Greek word for amber, electron. We begin our of electricity, the first chapter of electricity, electrostatics, and the static electrical charge at the rest. We know, here the figure two plastic roots then have been grouped with them to repel each other. And we know, and here this remaining root causes it become electrically charged. If we repeat the experiment with various materials, we find the all charged object fall into one of just two groups, and like the plastic root roofed with the floor, and those like the glass and root with the silk. And Benjamin Franklin explained this model in which every object has a normal amount of electricity can be transferred from one object to other when two objects are in the close contact. When and they are grouped together, this leaves one in here there. Leaves on with the excess charge, and other with the deficiency of charge in the same amount as the excess. And here this is figure in here, and the second figure, object carrying charge of opposition attract each other in here, each other attract between each other, and the first root, and here the first object, and rotational and clockwise. And the second figure B, and object carrying charge of the same sign or repel each other, and here this is positive, and this is each other and positive, and the same repel each other in here. We know, and we know the Coulomb's law, and we know the force exerted by one point charge on another along the line between the charge in here. This is we know, and Coulomb's torsion and balance. And the force exerted by one charge and another with the start charge Coulomb, using a torsion balance of his own invention. In here, this is Coulomb's experiment. Charge are very much smaller than distance between them, so the charge chooses the point charge. We know, and if we take maybe one electrical charge and second electrical charge, maybe and the positively we know, and maybe we take one electrical charge positively and negatively between two electrical charge, and have force, electric force, and the first and distance between two electrical charge and R, and the magnitude of the force of electrical force, and F equal K. This is Coulomb's constant, and Q1 multiplied by Q2 divided by square R. Square R and R, this is distance between two electrical charge, Q1 and Q2 electrical charge. Maybe we take positively, one positively and negatively. And here, and the value will be positive because the model of electrical charge. And K and the Coulomb is a constant, and approximately 9 multiplied by 10 power 9, and Newton meter square divided by Coulomb square. And here this is definition we know, and the result of experiments of Coulomb's, and here this is Coulomb's law, and here the definition Coulomb's law: the force exerted by one point charge on another acts along line between electrical charge varies inversely in the square of the distance separating the charge as the proportional to product of the electrical charge, we know, and the force proportional electrical charge, and the force in the repulsive of the, if the charge has the same sign, and attractive if the charge has opposite sign. And here this is the definition Coulomb's law, and here the Coulomb's law for the force exerted by electrical charge Q, and the second electrical charge second. And where in the here this is vector, and here this is vector point from Q1 to the second electrical charge, and this is unit vector pointing from Q1 and to Q2, but in here the vector R12 divided by R12. We know, and the gravitational force between two particles is proportional to the mass. We know of gravitational force to the mass of the particle, and it is always attractive, whereas the electrical force is proportional to electrical charge of the particle, and repulsive of both charge has some sign, and attractive if they have opposite, and the third electrical charge, electrical field intensity. We know, and here we started and study of chapter of the electricity and magnetism is the fourth chapter of electricity, electrostatics, and here we study electrical charge on the rest. And one charge produce an electrical field everywhere in the space, and this field at the position of the second charge, and the field propagates through space with the speed of light, speed of the light in vacuum. If a charge suddenly moves the force in the third on another charge at the distance R with doesn't charge until a time R divided by C later. And here this is a figure small test electrical charge, small test in here. This is test electrical charge. In the systems of charge Q1, Q2, and Q3, experience the force, and this is force between electrical charge Q1 and Q2, and this is direction of the from the one electrical charge Q1 to charge test charge, and here this is direction F3 and F2, and total electrical total force equal the first force, the second force, and third force, and equal the total force. Is the ratio we know, and the ratio of the electrical electrical force divided by test charge is the electrical field at that point. Electrical field at that point, and here the notation E. The notation E, and here we now the formula electrical field at the point, and F divided by Q0. Q is a small electrical charge, test charge. Test charge is small, and the figure shows this set point charge Q1, Q2, Q3, and arbitrarily arranged in this place. And if we place a small charge, test charge Q0, and will be force exerted on the test charge due to each other charge. And here the electrical field at a point in this force divided by Q0. And here formula of the electrical field. And here this is some electrical field in nature now, and the unit, the system international unit of electrical field and Newton divided by Coulomb. In the first column and the in Foucault called wire in radio waves in the atmosphere, electrical field, and sunlight, other things, cloud and lighting ball in X-ray tube, an electron of the in a hydrogen atom in the surface of uranium nucleus, and here this is value following electric following and the in radio phase and following and electrical field. 10 power minus 1 Newton and divided by Coulomb. We now and force in here exerted on the test charge and any point and related to electrical field at the point to the point Q0. In here, this is the formula the electrical force exerted on the test Q0 at any point in the any point. Okay, and we know of the electrical field, and we now and here maybe we take and F divided by Q0, and F and electrical field due to single point charge can be calculated from the Coulomb's law, and Q maybe Q1 and Q0. Q2 and Q0, Q3 and Q02. This is electrical field. This is Coulomb's law. But and F and replace on the electrical field at the point P due to charge. This and here this is formula and formula Coulomb's law for electrical field due to point charge in here. E0 is a unit vector pointing from the charge to the field point P. But and here maybe we take electrical field fields of the point charge and electrical field due to a distribution of point charge is found by summing the electrical field due to each charge separately. And here the formula of the electrical field due to a system of point charge in here, and the summing of electrical field due to each charge separately in here, the first electrical field plus second, third, etc., and plus final electrical field, etc. Okay, and here characterize electrical field due to the system of point charge. But we know, and here the figure A and so, and we can picture the electrical field by drawing line indicates its direction. At any given point, the electrical field is tangent to the line. Electrical field lines are the called lines of force because they show the direction of the force exerted on a positive test charge. And here this is direction line and line and force. And here or lines of force, or electric field lines, In here, the figure in here. This is figure and electrical field lines on single positive in here positive point charge. If the charge were negative, the role would be reversed. And here B figure the same electrical field line shown by beads suspends on oil. The electrical field of the charge object in the center induces opposite charge on the ends of each bead, causing the threads to align themselves parallel to the field. Yeah. And next, we take two electrical charge and two electrical charge positively, and when two electrical charge positively, and here the figure electrical field line due to positive point charge, the role would be reversed and both charge were negative. And for example, and the two electrical charge were 1 millimeter apart, and we are looking and from the point 100 kilometer away, they would look like a single charge in here. This information can also obtain direction calculation of the point in this region. And here we will take the figure show an electrical field line during an electric dipole. Electric dipole we know, and electrical dipole, this is system two electrical charge, one positively and negatively, very near the positive charge, and the lines are directed radially outward. Very near the negative charge, the lines are directed radially inward, and positive charge, the lines are already outward. The as I said, charge have equal magnitude. The number of lights that begin at positive charge equals the number that end at negative charge. Negative charge. In this case, the field is wrong in the region between the charge, and they indicate by high density of field lines in this region in the figure. In here, two and electrical field lines, or and electrical dipole, and B formula. Figure the same field line shown by beads of in oil. And here, and the question number four, motion of a point charge in electric fields. When a particle with a charge, electrical charge Q, as the unit of electrical charge Coulomb, they place an electrical field E. This experience force and Q electrical charge multiplied by electrical field intensity. Electrical field. If the electrical force is the only significant force acting on the particle has acceleration. In here, acceleration we know characteristics of the motion. The second characteristics of the motion are acceleration. Acceleration is a vector. Vector and acceleration equal the summing of force divided by mass, and force replace and electrical charge multiplied by electrical field. Where is the mass? And here this is mass of the particle. If the electrical field is unknown, and the charge to mass the ratio, and here charge and mass of the ratio, the particle can be determined from the measured acceleration. Because, and we know, maybe we take electron, if we take electrical charge of the electron, mass of the electron, electrical charge of the electron we know, and 1.6 multiplied by 10 power minus 19 Coulomb, mass the electrical mass of the electron, as a 9.1 multiplied by 10 power minus 31 kilogram. This is a small particle because it's a smaller mass. And the deflection of the electron, in uniform electrical field was used Thomson in 1897 to demonstrate the existence of electrons and measure their charge to mass ratio. If other examples of devices rely on the motion of electrons in electrical field are oscilloscopes, computer monitors, and television picture tubes, etc. And question number 5, calculating electrical fields from Coulomb's law. And here we describe the charge per unit volume. The first, here the volume charge density. Volume charge density is the notation, and rho equal electrical charge per unit volume, and delta V. Often charge is distributed in the layer of the surface of an object. We define the surface charge density sigma as the charge per unit area, and delta Q divided by delta A. This is area. Area, the unit of the area, square meter. We sometimes encounter charge distribution along a line in space. And the third, we define the linear charge density, lambda, as the charge per unit length. And here this is the unit meter, and the linear charge density, the system international unit, Coulomb divided by meter. And we show, and Coulomb's law is used to calculate electrical field due to various types of continuous charge distribution. We then introduce Gauss law, which relates the electrical field on closed surface, net charge within the surface. We use the relation to calculate electrical field for symmetric charge distribution. Okay, in here, and this is diagram. In here, and figure an element of charge dq. This is small dq and small element of the charge dq, small charge. Produces the field. And field in here, this is formula, D equal K dq divided by R square R at a point P. The field at P, and here this is positively charged, and here P. And field at P due to the total charge is found by integrating over entire charge distribution. And electrical field, we know formula, electrical field at a point P due to this charge given by Coulomb's law, and dq and the rho multiplied by dV. The small and element of charge, dq element charge, and rho multiplied by dV. And rho the charge density, volume charge density, and volume charge density, and replace in final formula here, electrical field due to continuous charge distribution, and integral from volume and q dq r square multiplied by r. And where the q and the r, the where is the charge distribution of the surface or line, we use maybe, and distribution on the surface or line. If we use on the surface, we the q equal area, and here sigma and surface density multiplied by dA. And maybe we take a line is if the charge is distribution on the line, and here we and the q replace and lambda multiplied by multiplied by the L, integrate over the surface or line here. And Gauss is the law, and Gauss is the law, and we the first we show electrical flux. The mathematical quantities that correspond to the number of field lines crossing here electrical field lines on uniform in here uniform field crossing an area that perpendicular line to and area perpendicular to the field and line in here the product and here electrical field flux in here because one line and the or maybe 1,000 line and we using electrical flux and the mathematical quantity corresponding to number of field lines crossing this a surface is called electrical flux. Electrical flux F, which is the for a surface perpendicular to electrical field, is defined in the formula. And here the electrical flux, electrical field multiplied by area, and unit of the flux and newtons multiplied by square meter and divided by Coulomb in here. And the second formula, the second feature, electrical field lines and uniform electrical field. The perpendicular to area A1 in here are perpendicular, but makes an angle theta with unit vector m. When an electrical field is not perpendicular to the area, the flux, and electrical field multiplied by area and maybe and En here equal electrical field multiplied by cosine, and this is angle between and n vector n and electrical field. This is between En equal E multiplied by cosine theta in here. The flux through area A2 in here and the same as the flux through A1. And final formula and electrical flux and electrical field M multiplied by A and this is A cosine theta and the electrical flux. And here the definition of electrical flux in here, electrical flux, limit delta A approaches 0 and the sum and vector n multiplied by changing area and integral and s from s and here s area. And electrical field multiplied by dA and A. And the integral definition of electrical flux into. And maybe we take a spherical surface, enclosing the center point charge and the center electrical charge and then from electrical charge to surface, and this is radius. They are reduced and electrical field on the surface and has magnitude and electrical field kq r square r. This is radius of the sphere. Q electrical charge, positive electrical charge. K the Coulombs is a constant. But and electrical flux we using formula electrical field multiplied by area. Electrical, and here this is electrical field kq divided by square r multiplied by 4p r square. This is area of the sphere. Area of this sphere. And final formula and k in here. R square and final formula for p k and q. For p, this is a constant, k is the Coulomb is a constant, q electrical charge, and here positive electrical charge and put on the center sphere. Okay, and here and this is we take one electrical charge Q3 and one surface enclosing point charge Q1 and Q2, but not Q3 and Q3 on the space. On the space is the net flux through this surface, is the surface net flux on 4P K Q1 and Q2 because and the electrical field and the enclosing point charge and Q3 is not but not Q3 and we not use under the electrical charge 3 but and using electrical charge Q1 and Q2. And we now and formula the net flux through and the surface equals 4pk times and net charge inside and here and 4pk q inside and here this is formula Gauss law, but the net flux the surface, the power equals 4pk q1 and q may be positive, negative, or zero, depending on sign and magnitude of the two charges. In here. Okay, and Gauss is the law, and this Gauss is the law. It's validity dependence on the fact. Electrical field due a single point charge varies inversely with the square on the distance of the charge. It was the property of electrical field made it possible to draw fixed number of electrical field lines from charge and have the density of lines be proportional to the field strength. And permeability, permittivity of free space K equal and K in the columns and here K is the column, the constant. Permittivity of free space is called epsilon 0, the constant. Epsilon 0 is electrical, the constant. And here the K equal 1 divided by 4p0. Epsilon 0 is the electrical, the constant. 8.85 multiplied by 10 power minus 12 Coulomb square divided by Newton divided by Newton multiplied by meter. And K and Coulomb is a constant, approximately 9 multiplied by 10 power 9 Newton meter square divided by Coulomb square. And using the notation in here, the formula Coulomb's law for electrical field is written in here. Coulomb's law in terms of epsilon 0 in here, epsilon 0, and maybe using and the last page we're using and K in here. This is and K replace 1 divided by 4p epsilon 0. And Gauss law is written in here Q and this is the and closed surface closed in here closed surface and closed surface and electrical field multiplied by area and final formula inside electrical charge divided by epsilon 0. And here the Gauss law in terms of epsilon 0. And plane in here Gauss the surface for calculation. In here Gauss the surface the calculation of electrical field due to an infinite plane of charge in upper and lower faces on this field box. Electrical field perpendicular to the surface. It is a constant in magnitude. And we're using and here electrical field near an infinitive plane of charge. And formula sigma divided by 2 epsilon 0 maybe 2p k and sigma 2p k and the sigma in here. And here electrical field due spherical shell of charge. We know and flux in here and flux through the surface and electrical field on there and the spherical surface on the spherical 4p square. This is area is the surface or this is area of the of the air, closed sphere, sphere and spherical Gaussian surface of radius for the calculation of the electrical field outside a uniformly charged spherical shell of radius r. Okay, and we are electrical field outside and spherical shell of charge outside electrical field intensity Q KQ divided by square R, K and replace 1 divided by 4 P epsilon 0. And inside of spherical shell, electrical field equals 0 because inside electrical field in spherical shell. Outside we're using in here so formula. Maybe in here outside, yeah, inside in here this air in here equals 0, and here this is, and inside and electric field equals 0, and outside in here electrical field, this is formula using outside the spherical shell of charge. And here we know formula of the electrical field intensity. This is formula electrical field. And electric field proportional 1 divided by square r. And here this is line following electrical field proportional 1 square r square, because equal therefore in here r inside electrical field equals 0. When if we take air outside from outside electrical field intensity and following curve in here, this is formula following, this is formula in here, this is this is curve, okay. And there in here this is final page, and we now in here today, and we studied and electrical chapter electrostatic, electrical charge, and Coulomb's law to electrical charge maybe positively or negatively, and the force attract between two electrical charge positively or positively and negatively, etc. And characteristics of electrostatic field. The first characteristic, electric field. There we studied definition of electrical field and different formula of electrical field for the different maybe a sphere, maybe and sphere plate and two parallel plate, one plate, and charge with a positively or negatively, etc. And here this is the second, the final, and we write a formula of the Gauss theorem, and Gauss theorem relationship with the different configuration object. Thank you for attention.